All right, Priya P, let's do some rice table stuff. You ready? I am. Let's do it. So what is a rice table and how is it going to help me in stoichiometry? Well, it can help you when you're working with limiting reagents or reactants and working with shifts and equilibriums. This is just a way to actually organize this stuff in a nice table. The actual calculations for equilibrium are way beyond the scope of this course, but understanding this kind of stuff will really help you, especially if you intend to take any upper level chemistry classes, and they'll also just kind of help strengthen your math skills. So, boom, there's a plus. Okay, so what is a rice table? It's a way to organize information regarding the moles of substances in a chemical reaction. So the mnemonic device that we are using here, RICE, R-I-C-E, stands for reaction ratios, or just ratios. I is for initial conditions. C is for changes during the reaction. And then E is for endpoint conditions of the reaction. So ratio, initial, changes, endpoint. Got it? Good. So this is how you set up your RICE table. The RICE goes on the left-hand side, and across the top is your reaction or your chemical equation. That's already balanced, you can see. So we have potassium phosphate reacting with calcium chloride to produce potassium chloride and calcium phosphate, right? So what you're going to write is the ratio. So how many moles there are reacting in a balanced equation. So there you're just putting down the coefficients of the balanced equation, 2, 3, 6, and 1. Okay, that's when it's balanced. That is the ratio. So that is the ratio in which they actually react. Can I say ratio one more time? Ratio. Ratio. Got it. So the initial conditions identify the number of moles of each substance that is available for the reaction. Before you start the reaction, you can't have products. So we already know that initially there are 0 moles of the products. Okay? So we can go ahead and fill that in. So let's say we're looking at this problem right here. Okay, you look at your problem and you find out how many moles you start with, if anything. So if they give you grams of potassium phosphate and calcium chloride, you actually would have to convert them to moles. But you guys already know how to do that. You're experts. For the purposes of this example, we'll just say that we have 2.4 moles of potassium phosphate and 2.7 moles of calcium chloride that we're working with. So those are our initial conditions. So what we need to do is we need to fill out our RICE table. So unless you can already identify the limiting reactant or you already have done it in a previous step, assume that the reactant that's listed first is the one that is limited, or the limiting reactant. So if true, all of the reactants will be completely used. Okay, so ending up with negative amounts on the endpoint is a bad thing. All right, so if you make a mistake, your RICE table will let you know. So let's say that potassium phosphate is the limiting reactant, okay? And we use up all of it. We write on that change part minus 2.4 moles because obviously if it's the limiting reactant, we're using all of it, right? So what we're concerned with is if I use all of that, how much calcium chloride did I use and how much potassium chloride did I make and how much calcium phosphate did I make? Well, let's figure that out. Let's carry out the changes. Well, since there is a 2 to 3 ratio between the two reactants, if I use 2.4 of potassium phosphate, I must have used 3.6 of calcium chloride. Now some of you are looking at it going, wait, you only had 2.7 of calcium chloride. How could you use 3.6? Bingo, we found our mistake. All right, so I can't end up with negative moles. So what does that mean? That means that, oops, let's change it. We must have had it wrong initially, and calcium chloride must be the limiting reactant. So you see how quickly that just sort of worked itself out before we even did any more calculations. So now we're going to assume that we used all of the calcium chloride because that is our limiting reactant. So we write minus 2.7 moles. All of that gets used up. You start with 2.7, you lose 2.7, your endpoint E is 0. Now, since calcium chloride and potassium phosphate react in a 3 to 2 ratio, we got to convert that 2.7 moles into a 3 to 2 ratio here to see how many moles of potassium phosphate we used. Once you perform that calculation, you actually just multiply 2.7 times 3 over 2. Sorry, my fault, times 2 over 3, and you end up getting 1.8. So we used 1.8 moles of potassium phosphate, and that leaves us with 0.6 moles. Great. One of them's all used up. One of them has some excess remaining. So how many products did we get? Well, what we have to do is we have to determine the amount of products using mole ratios for potassium chloride and calcium phosphate. So since they are products, they are added to the system. So they have positives in front of them, right? So if we used 2.7 moles of calcium chloride, then how many moles of potassium chloride did we get? Well, they react in a 3:6 ratio, which actually we can see is a 1:2 if you reduce that, and then 3:1 ratio for the calcium phosphate. And if we do those calculations out, 5.4 and 0.9 moles is what we get. So therefore, our theoretical yields are 5.4 and 0.9 moles, respectively, for those two products there. Okay, so hopefully this all makes sense. This is actually quite an easy way to make sure you get all of this down. Okay, so hopefully you guys got it all together, and good luck on the rest of your journey, I guess. Gosh, so awkward.